In this video, we're going to lay the groundwork for analyzing op-amps by talking about appropriate models for op-amps and how those models can be used in feedback analysis. Just as a reminder, this is what op-amps look like. They're chips that we see in the lab, and in schematics we draw them as triangles. We've seen this equivalent circuit model for op-amps before, but we haven't talked about it in detail yet. We're going to do that on this slide. The resistor on the left is easy enough to understand. It suggests that some current flows from V plus to V minus when the voltages are different. However, the diamond-shaped device on the right is a new symbol. It's called a dependent voltage source, and it just means that it produces a voltage that is set by other values in the circuit. In this case, the voltage is A times V plus minus V minus, which is a byproduct of tricky circuits inside the op-amp that we talk about in biggies. The dependent source is attached to ground on one side and the output on the other side, which is just telling us that the V out voltage is always generated relative to 0 volts. The big trick with op-amps, as suggested by the text on the slide, is that A and Rin are both extremely large. For reference, we use devices with Rin that are about 2 gigaohms in this class, and A tends to have a value of around 10,000, but it's highly variable with manufacturing and temperature. You can't count on A to be a specific number, but you can count on it to be very big. We'll regularly approximate both A and Rin to be infinite. You'll see in lab that these are actually really good approximations. One reason that op-amps are super interesting is that they implement classical feedback loops. You'll notice that the output is equal to A times V plus minus V minus in our equivalent circuit model. That's the same thing as saying that our output is produced by some error signal, which is the difference between V plus and V minus, passing through a gain block with value A. So op-amps are essentially proportional control in a box, which is a really handy tool. To show how op-amps can be useful, we'll want to test drive this op-amp model. This slide sets up a scenario where an op-amp could be useful. Here we're trying to measure the output of some sensor, which generates a small voltage and has a large 100 megaohm series resistance. This is characteristic of most transducers. For instance, a piezoelectric vibration sensor. The equivalent circuit model for a multimeter, which you may recall from earlier videos, has an input impedance of 10 megaohm. We can stick our sensor model and our multimeter model together and use that to calculate V measured. And I'm going to stop talking for a second and give you a chance to try that. So the answer is that V measured would come out to be 1/11th of a millivolt, or about 90 microvolts, because you have a resistor divider between this 10 megaohm load and the 100 megaohm source resistance of the sensor. That's about 90 microvolts, which is way too small for our multimeters to read. The big issue here is that our multimeter is having a nasty loading effect on the sensor. Okay, so I've promised that op-amps are going to help this problem somehow or another. So let's put an op-amp between our sensor and the multimeter. The first thing to figure out is summarized in question 1 in the lower left here. Does Rin load the sensor? Or put another way, does adding the op-amp still load the multimeter? Take a second to answer it yourself. The answer is no. In this case, V plus is formed by a divider between our sensor and Rin, and because we approximate Rin as infinitely large, V plus is going to be equal to V sensor. The second question is whether we can infer what V sensor was from V out, which we can safely measure without loading the op-amp. So take a second to calculate V out. You should have come up with the answer positive or negative infinity, depending on whether V sensor was bigger or smaller than 0 volts. In this case, V minus is 0 volts and V plus is V sensor, so V plus minus V minus is just going to be equal to V sensor. However, A is infinite, so we wind up with positive or negative infinity volts at the output. Even if you assume A is finite, we don't know exactly what A is, only that it's big, so we can't infer V sensor from V out. Also, a quick reminder, even if A is very large, the op-amp doesn't actually generate an infinite output voltage. It clips its output at the positive or negative power supply, which is a behavior referred to as railing out. This behavior trips up a lot of students because this op-amp diagram omits power supply connections. It's easy to forget that they're there. If your output is stuck at a constant value, then it's probably railing out. Obviously, this behavior doesn't help us with our current problem. If your voltage is always equal to your power supply voltage, then you can't infer anything about V sensor. That means this op-amp configuration doesn't quite do everything we need. However, this configuration doesn't use any feedback. It's in a configuration called open loop, because the output isn't connected back to the negative input. And we observed earlier that op-amps are really good at implementing feedback loops. Maybe some feedback will help. So this circuit seems great. It's an ideal impedance buffer. We've made a copy of V sensor that can drive any impedance without loading problems, and also without loading V sensor in the process. Because it has a gain of 1 and we use it to buffer impedances, we usually call this a unity gain buffer. We're not going to dig deep into this because it's not the focus of this class, but you can get to the same result using the feedback theory you learned in E79. If we put a feedback factor of 1 between Vout and V- in the feedback model of the op-amp from earlier, then we can use Black's formula, which says that the closed loop gain is equal to the forward path over 1 plus the loop gain, to discover that the gain from V plus to Vout is about 1, as shown here. So in summary, the op-amp equivalent circuit can be broken down to two major features. They have an extremely high input impedance, which means they don't load anything, and they have an extremely high gain, which means they need to be used in negative feedback. And that gain specifically amplifies the difference between V plus and V minus. You can use that to analyze op-amps, and we've come to a few general conclusions about that. One is that open-loop op-amps rail out. They generate voltages that are way too big, because the gain isn't controlled, and you can't figure out anything about V plus and V minus from them. Two is that closed-loop op-amps in negative feedback can be analyzed and seem to give us good results. And the good result that we specifically saw is that unity gain buffers, which just connect the output to the negative input, are really easy op-amp circuits that make an ideal impedance buffer.